Good morning, all of you. This is lecture of field theory. Chapter first, field extensions. We have seen first example. Question: prove that D divides N if and only if field F P raised to D containing field F P raised to N. Solution: here we have given first field is containing P raised to D elements and second field is containing P raised to N elements. Now we will see the proof. Given D divides N and P is prime. We know result. D divides N if and only if x raised to D minus 1 divides x raised to N minus 1, where D and N belongs to set of integers. If and only if P raised to D minus 1 divides P raised to N minus 1. Now we will take these elements P raised to D minus 1 and P raised to N minus 1 as a power of x. This implies that x raised to P raised to D minus 1 divides x raised to P raised to N minus 1 minus 1. We can check this is part of number theory, which is if and only if part. Multiply both sides by x. We will get x raised to P raised to D minus x divides x raised to P raised to N minus x. This implies that x raised to P raised to D minus x is a factor of x raised to P raised to N minus x. Also, this implies that all roots of x raised to P raised to D minus x are the roots of x raised to P raised to N minus x. If all the roots of x raised to P raised to D minus x are the roots of field F P raised to D, therefore these all roots must be containing field F P raised to N. If and only if field F P raised to D is containing field F P raised to N. Here we can use theorem D divides N if and only if x raised to D minus 1 divides x raised to N minus 1, where D and N belongs to set of integers. We have here proved that D divides N if and only if field F P raised to D which is containing field F P raised to N elements. Next we have seen definition. Point is cyclotomic polynomials and extensions. Definition: U of n denotes the group of nth root of unity over Q. And above result, we have seen that D divides n if and only if U of D is subgroup of U of n. This means that 3 divides 6, then the group of third root of unity is subgroup of group of sixth root of unity. Therefore, similarly we can say that fourth root of unity contains second root of unity. Again, 10th root of unity is contained fifth root of unity, and so on. This is important result. Then next we have seen another definition. Define nth cyclotomic polynomial phi n of x to be the polynomial whose roots are the primitive nth root of unity. That means that nth root of unity, that is x1, x2 up to xn, which are n elements. Now we will check primitive nth root of unity. That means primitive means generators. Some element has generators and some element may be not a generator. There are some element, they are generator of these groups. We are taking only those roots which are generator of this group, that is set of primitive nth root of unity. Then phi n of x equal to product of x minus xi, where xi is primitive group of nth root of unity. That is, here we have checked this information that set of nth root of unity forms a subgroup, and again check this groups is cyclic group and it has a generator. This is part of group theory. Suppose A is root of some cyclic group, then A raised to n is also group if and only if GCD A with n equal to 1. This result implies that phi n of x equal to product of 1 less equal A less equal n and GCD of A with n equal to 1 into x minus xi n of raised to A. Here we written xi n. This implies that xi n goes to nth root of unity. Here we also mention that if xi is a root, then xi raised to A is again primitive roots if GCD with A with n equal to 1. Here it is clear that degree of phi n of x equal to phi of n, where phi is Euler's functions. We know that how many numbers which are relatively prime to n and which are less equal n. Then there are only phi of n elements. Phi of n numbers, therefore phi of n numbers of this linear factor and product of this factor we give degree of phi n of x, where phi is Euler's functions. Let x raised to n minus 1 equal to product of xi belongs to nth root of unity, that is u of n, and xi raised to n equal to 1 into x minus xi. Here we observe these two are different. Phi n of x, that is phi n of x taking only factors of primitive roots, while we take x raised to n minus 1 roots, then we give all nth root of unity. If we group together the factors x minus xi, where xi is an element of order d in u of n, that is group of nth root of unity. Therefore, we obtain x raised to n minus 1 equal to product of d divides n into product of xi belongs to u of d and xi is primitive roots into x minus xi. We are taking dth root of unity, where d divides n and varying d. Therefore, the inner product is phi d of x. Therefore, we can write x raised to n minus 1 equal to product of d divides n into phi d of x. Suppose n equal to 4. We know that divisors of 4 equal to 1 to 4. 1 to 4, 1, 2, 4 are divisors of 4. Then we can write x raised to n minus 1 equal to phi 1 of x into phi 2 of x into phi 4 of x. This equal to x raised to 4 minus 1. Here n equal to 4. Also, we denote that n is equal to summation d divides n phi of d. We have seen this is part in last time in number theory. Then next we have seen lemma 14. Lemma 40 statement is the cyclotomic polynomial phi n of x is monic polynomial in Z over polynomial x of degree phi of n. That is solution. We will prove that this cyclotomic polynomial is monic polynomial. From above result, from definition of phi n of x, we know that phi n of x equal to product of xi belongs to u of n. U of n means set of all nth root of unity and xi is primitive roots into x minus xi. Then phi n of x equal to product of 1 less equal a less equal n, and GCD of a with n equal to 1 into x minus xi n raised to a from above definition. Then phi n of x is monic and degree of phi n of x equal to phi of x, where phi is Euler's phi function in above result. Then we have also proved that phi n of x belongs to Z over polynomial x. Here we will prove this result by using mathematical inductions. First, now for n equal to 1. This implies that phi 1 of x equal to x minus 1 belongs to Z over polynomial x. Here 1 is generator of 1th root of unity, that is primitive root. 1 is here primitive roots. Therefore this result is hold for n equal to 1. Then second, now we will assume result is hold for all m less than n. That is, we assume m equal to n. That is phi m of x belongs to Z over polynomial x for all m less than n. Then for m equal to n, we know that x raised to n minus 1 equal to phi n of x into f of x, where f of x equal to product of d divides n and d is less than n into phi d of x. By induction hypothesis, f of x belongs to Z over polynomial x. Since f of x divides x raised to n minus 1 over q of xi, and both f of x and x raised to n minus 1 are in q over x. Therefore, f of x divides x raised to n minus 1 in q of x. By Gauss lemma, we know that Gauss lemma, f of x divides x raised to n minus 1 over z. Therefore, alpha is a root of some monic polynomial over q. Then alpha must be a root of some monic polynomial over xi. It must be an integer. Then this implies that x raised to n minus 1 or x raised to n minus 1 divides f of x equal to phi n of x belongs to Z over polynomial x. Hence we have proved that phi n of x is monic polynomial and it is also in Z of x, degree is phi n. Hence the proof, that is, the cyclotomic polynomial phi n of x is monic polynomial in Z over polynomial x of degree phi n. In this lecture, we have seen that what is meant by cyclotomic polynomial, what are different notation to write cyclotomic polynomials, what is phi of d, polynomials, and some of the properties. Thank you.